Welcome back, focused learners. Okay, so today's explainer is, well, honestly, it's basically an engineering heist. We're looking at how developers literally resurrected ancient number theory to tunnel directly under the rigid, uncompromising constraints of the Ethereum virtual machine, or EVM. If you've ever wondered how the true next generation of decentralized networks actually operates under the hood, you are definitely in for a fascinating ride today. Okay, let's dive into this. I want you to keep this massive, honestly impossible-sounding question in your head as we go. How do you execute complex, fluid trigonometry on a global computer that literally cannot understand decimals, right? It sounds completely impossible. But, the push for the absolute cutting edge of on-chain finance forced developers to figure it out. And the solution they found? It completely reimagines how we process math on a blockchain.
So Section 1, the impenetrable wall, the floating point problem.
All right, here's the fundamental issue. The EVM cannot process native floating point math. It just doesn't do decimals. And it certainly doesn't do continuous trigonometric curves like sine or cosine. To really grasp why this is such an impenetrable wall, we kind of need to personify the hardware inside your computer. On side A, we've got the floating point unit, or what we'll call the FPU gambler. Now, the gambler is incredibly fast, sure, but it relies on probabilistic, lossy guessing to simulate those continuous curves. It's basically just throwing darts at a board. But over on side B, we have the arithmetic logic unit, the ALU surveyor. Now, the surveyor is strict, it's discrete. It relies on 100% deterministic, exact verifiable arithmetic. 1 + 1 = exactly 2, universally, every single time. And the thing is, decentralized systems absolutely require that exact truth of the ALU surveyor.
And this brilliantly illustrates why relying on the FPU gambler is so dangerous on-chain. Researchers actually call the fallout from these hardware approximations the wood chipper effect. Because when non-deterministic hardware just guesses the math using decimals, the exact path of that data, its mathematical identity and provenance, is permanently destroyed. It's literally like throwing your data into a giant blender. You can never perfectly reverse engineer the math once it's been approximated. And on a blockchain, that shredded data leaves liquidity pools incredibly vulnerable to rounding errors and just brutal arbitrage exploits.
Moving on to Section 2, casing the joint, deconstructing Uniswap v3.
Before we get to the big breakthrough, we really need to examine the legacy blueprint. See how early protocols tackled this exact problem. Let's deconstruct Uniswap v3. So, to track fluid markets without native floating point math, the protocol invented ticks. These are discrete price intervals that chop up infinite potential prices into a rigid integer grid. And they map this space using a hard-coded logarithmic formula, basically 1.001 to the power of I. But well, here's the catch. Real, complex liquidity just doesn't fit neatly into square ticks. It's like trying to force a smooth, continuous curve into blocky Cartesian grids. Navigating that grid sequentially requires heavy FPU approximations, and that causes severe computational bloat and just massive gas spikes during high market volatility.
Now, what's really interesting about this slide is the massive discovery made in the bestape/mmtest GitHub repository. Developers essentially proved that Uniswap's famous tick math library isn't some foundational absolute. It's actually just one highly specific, hard-coded use case of a much broader mathematical theory called base-scale calculus. While Uniswap forces these rigid Cartesian boundaries, base-scale calculus defines the price-tick relationship using the fluid, generalized theory of Pythagorean triples. We're literally talking side A, side B, and side C of a right triangle. This insight cracked a door wide open. It let developers view automated market makers through the lens of pure number theory, which completely eliminates that approximation debt.
Which brings us to Section 3, the secret tunnel, the generative method.
So instead of dragging around all that complex Cartesian math, developers found this incredibly elegant shortcut. The secret weapon here is a single linear integer recurrence. Specifically, sequences like the Pell-Lucas numbers, which are formerly cataloged as OEIS A001333. Instead of using messy decimal approximations for irrational numbers, like say the square root of 2, the mtest repo utilizes pure integer sequences. You just take integer ratios that form a sequence of convergence, and they provide incredibly accurate approximations using purely verified integer logic. Absolutely no decimal points, no floating point guesswork. They're basically tricking the EVM into calculating mathematically verifiable constants on the fly, right there directly on the EVM, using nothing but simple arithmetic. It's wild.
Let's move to and see how this builds a complete roadmap for full generalization, just like they outlined in the repository. Step 1. Parameterize the base.
They modify the library to accept the parameters of the Pythagorean base's inputs rather than relying on those hard-coded constants. Step 2. On-chain generation. They replace those static approximation values with the Pell-Lucas integer recurrences to generate mathematical constants dynamically, entirely on the fly. And finally, step 3, gas optimization. Because they're using an iterative loop of simple arithmetic rather than complex formulas, it is so much more gas efficient, making it perfectly tailored for the EVM.
To really anchor all this abstract math, let's look at a tangible victory from their solidity experiment. By using just simple, exact integers, specifically taking the sequence out to 10,202 over 101, the system achieves a ridiculously minuscule error rate of just 0.00485%. It converges almost immediately, and they achieve this incredible precision without ever asking the hardware to make a single guess. I mean, it is quite literally on-chain magic.
All right, section 4, the escape, absolute hardware determinism.
By ditching the FPU gambler entirely and moving exact integer geometry onto the blockchain, developers achieved absolute hardware determinism. Because the math is now perfectly exact and completely free of rounding errors, it allows the system to utilize a LIFO, or last-in, first-out ledger engine. Think of this engine like an incredibly efficient bouncer at a busy club. It doesn't care about the whole line wrapped around the building. It only queries index 0, the person standing right at the front of the line. And this unlocks insanely efficient single-entry bookkeeping. It instantly verifies the absolute state of the math without dragging through a massive history of past transactions, which guarantees a flawless, non-halting digital history.
When you stack all of this up, the integer recurrence, the exact base scale calculus, the deterministic ledger, the impact is staggering. This mathematical shift yields a 74 times reduction in metabolic computational energy. Because they bypass complex trigonometry entirely, the energy required to perform these exact coordinate operations drops to an astonishing 0.05 picojoules. It completely obliterates the massive gas costs that choked legacy systems.
So the crucial point is perfectly captured by this really profound quote from the architecture documentation. We move from approximating a curve to possessing the state of the manifold. Think about that. We aren't just approximating reality with messy, broken decimals anymore. Because the system uses exact integer identities, the machine isn't guessing where the data is. It absolutely knows. It physically possesses the exact, indisputable mathematical truth, completely eliminating the lossy observer debt of the past.
It truly is incredible to see how pure, ancient number theory can just step in and solve some of our most absolute modern computing constraints. We've traced this heist from the impenetrable wall of the EVM, through the generative tunnel of Pell-Lucas integers, all the way to absolute hardware determinism. So I want to leave you with this final, deeply provocative question to ponder. Now that we have the tools to mathematically possess the exact state of a system without guessing, what will you build next? Thanks for joining me for this explainer, and I'll catch you next time.